In our previous video, we went over some of the terminology used in radiometric dating. And we also went over some of the important concepts, like when there's a radioactive parent isotope in a mineral, the amount of the parent isotope is going to decrease over time as a result of radioactive decay. And for every atom of parent isotope that decays, a stable daughter isotope is formed. So one atom of parent radioactive isotope decays, one atom of stable daughter isotope forms. So as time goes on, the amount of parent isotope in a mineral will decrease as the amount of daughter isotope in the mineral increases. The ratio of parent isotope to daughter isotope is going to change in a systematic way. So just to put things in a little more concrete terms, we want to show how in an igneous rock, the amount of parent isotope is going to decrease and the amount of daughter isotope increase over time, and how the ratio of parent to daughter isotope changes over time. So we're going to take a very simple example, igneous rocks, and we know that all igneous rocks form from the cooling and crystallization of magma. What we have in this diagram here is, imagine a magma, it's all liquid, and the little red dots represent atoms of radioactive parent isotope, and the green dots represent the stable daughter isotope that forms from the radioactive decay of that parent. I mean, if you have these radioactive parent isotopes in the liquid magma, you're going to have some daughter atoms in there too because of the decay of previously existing radioactive parent isotopes. Well, let's say this magma begins to cool and we start to have minerals crystallize out of the magma. That's how the igneous rocks form. Let's say we have a mineral that's crystallizing out of the magma, and it's only those parent radioactive isotope atoms that are the right size and the right charge that they can fit into the crystal structure of this mineral that's forming during the crystallization process. Let's see what happens. In this case, we're assuming that only the parent isotope atoms, the red ones, are the right size and charge to fit in the mineral crystal structure, and the stable daughter isotopes, they're not the right size or whatever, they don't fit in, so there's none of those trapped in this mineral when it crystallizes. So we're focusing in on two crystals of that mineral, and we could just count up the number of parent isotopes that are trapped in each of these crystals, and there's 1, 2, 3, 4, 5, 6 rows down, times 2 is 12, and there's 2 of them, so there's 24 parent atoms that have been trapped in this mineral. I say trapped because the mineral crystals are solid. The idea is that once they're in that mineral crystal solid, they cannot get out. So we're going to call this time when the magma is cooling and crystallizing, our mineral is forming, and the whole igneous rock is forming at this same time, basically. We're going to call this time 0, or T equals 0. And what do we have in our minerals? We have 24 atoms of parent isotope and 0 atoms of daughter isotope. Well, now let's let time pass by. Everything's solid. And let's say we have a whole half-life go by. Remember, the half-life is the time it takes for half of a radioactive parent isotope to decay. So here we're looking at those same two crystals after one half-life has passed. How many red or parent atoms are in there? 5, 6 times 2 is 12. So there's 12 remaining in there. There was 24, so that makes sense. We only have half left. What happened to the other 12 parent isotopes that were in there when the mineral crystallized? Well, they became daughter isotopes. So we have 1, 2, 3, 4, 5, 6, and 6 is 12 daughter isotope atoms in those two mineral crystals now. So let's call this time 1. We're going to have these time increments go by in half-lives. We were at 24 parents at time 0. Now here, after one half-life, we only have 12 parent isotopes. 12 daughter isotopes have formed from radioactive decay of parents, And what's our ratio of parent to daughter isotope? It's 1:1. Let's let another half-life pass by and take a look at those two same mineral crystals. Well, another half of the parents are gone now, so we have just 6 parent isotopes remaining. And how many daughter isotopes? Don't say 6. It would be 6 from the 6 parents that decayed in this step, plus the 12 that are still in there. So at time equals 2 half-lives, if you count them up, we have 6 parent atoms remaining in our mineral crystals and 18 daughter atoms. The idea here, or really it's an assumption, is that the stable daughters formed within the solid mineral crystal. So once they form, they can't get out. Just like we said, the parents can't get out. What's our ratio of parent isotope to daughter isotope? 1:3. Now, what if we would go another time step to 3 half-lives? Well, we'd lose another half of parent atoms, so we'd be down to 3 parent atoms. And then how many daughter atoms would we have? We would have the 18 that had been there already, plus the additional 3 that formed from radioactive decay. So that would be 21, right? So let's make a little table here and show what we've seen. At time 0, remember, that's when the magma cools and crystallizes. We had 24 parent isotopes, no daughter isotopes. After 1 half-life, we have an equal number of parent and daughter isotopes. Our 1:1 ratio is going to hold after 1 half-life. That's going to be the case, 1:1 ratio, as long as we have this case where no daughter atoms were trapped inside the mineral when it crystallized. We saw in the little drawing that after 2 half-lives, our ratio of parent to daughter isotope is 1:3. And we were just calculating that after 3 half-lives, our ratio of parent to daughter would be 1:7. And these ratios are always going to hold like that, again, as long as there were no daughter isotope atoms trapped in the mineral when the mineral crystallized. So that is a kind of a special case. We know the minerals that can take in these radioactive parent isotopes. We know the chemistry, the chemical makeup of our minerals. It's not always the case that no daughter isotopes are trapped in the mineral when it crystallized. And there's another form of radiometric dating called isochron dating that's used when that's the case. But here we have the simple case, we have a special case where the mineral that was crystallizing trapped only the parent isotope atoms when it formed. There's another assumption that we've been using, and I've mentioned, is that we assume that once the mineral crystallized, no parent atoms could escape from the mineral, and no daughter atoms could escape from the mineral either. Another assumption, really I didn't write it down, but another assumption is that no parent or daughter atoms can leak into or, sneak into our mineral crystal once it's crystallized. That's not always the case, because when rocks down in the crust get heated, the bonds between the atoms in the crystals start to begin to break, and you can get some leakage of parent or daughter isotopes into or out of the mineral crystals, and that will completely mess up the radiometric dating if you're trying to use this thinking or method that we're showing here. However, that isochron dating method, when that is done on the minerals in an igneous rock, you can actually tell whether there was some kind of heating event. You have to look for another rock to do your radiometric dating if there was some kind of heating event and you got leakage of parents or daughter atoms after the mineral crystallized. Well, I hope that makes sense. Now, what I want to do in the next brief video is show you a more practical example, or an example of a question that you might be asked on a test that applies this thinking that we've been going over in this video here to actually doing a radiometric dating analysis on a particular mineral in a rock to find out how old the rock is.